First Spin. Welcome to First Spin, a show where I learn how to use the Parallax propeller without having any prior programming experience. And rather than do this on my own, I have enlisted the help of two experts.
Hello, everyone.
Hello, Roy.
So this week, Addie wasn't really feeling industrious enough to actually come up with any questions, but she did put up.
Talk about the sound pill.
She did put up a post in the Parallax Forums.
Yes.
Asking if any of you guys had any questions that we could address.
And it is complicatedly called First Spin Ideas? ?
Okay.
Right. Just asking folks for ideas.
On the forums.
On the forums, correct. And we got some great ideas, actually.
Yeah. Some of which are a little more beyond the scope of First Spin, but some of them are
spot on
to discuss. Yeah.
Right. So RW Guest Logic Design wanted to know about pulse width modulation and counters, if that's not too advanced. So in terms of pulse width modulation and counters, we've had a episode on counters where Roy probably gave 5 different ways of explaining how counters worked.
So we're going to be repeating ourselves a bit, but go back and listen to that episode, and you'll get a lot of good material. Right. You'll have to suffer through Addie not getting it, but
your brain, my brain just didn't. I just didn't get. I was like, what?
And
Bits?
Hopefully Addie can put a link to that episode in the description.
I will do that. And then we covered a little bit of pulse width modulation and counter use in pulse width modulation for our servo episode. But servo pulse width modulation is slightly different than duty cycle pulse width modulation.
Well, yeah. I mean, servo pulse width modulating is kind of interesting because you're sending out a pulse once every 20 milliseconds.
Right.
And not a continuous pulse that you're varying the on and off range or just the frequency.
Right.
And so there's two ways to do PWM. The most useful and common one for a lot of things is the duty cycle one, where you're determining how much time the pulse is on versus off for a given frequency of updating.
Right. So the way I thought about this was pulse width modulation, servo pulse width modulation was 1 millisecond on, 20 milliseconds off. 1.2 milliseconds on, 20 milliseconds off. 3 milliseconds on, 20 milliseconds off. So
except for 3 is out of range.
Well, yeah. I mean, just that.
2.
My idea was the pulse itself changes. The pulse's width changes. But the space in between is exactly the same.
Yeah,
and that's different.
It's actually
when you're changing the duty cycle in regular pulse width modulation, the distance between one full pulse on and off and the length of the next full pulse on and off are always the same.
Exactly the same. Right. So duty cycle is more like 30%, 70%, 20%, 80%.
Right.
10%, 90%.
On
so it always
versus off time.
It always goes to 100% for each cycle.
He's asking about how to do this with counters.
Right. Yeah. Which we did counters with the servo type of pulse width modulation, and that was, I think, Roy.
But it was sort of a special case usage of the counters because you set up the counters in a certain slow mode and then just reset them manually to get that 20 millisecond pulse rate.
Right.
The normal way of setting them up is to, for driving motors or LEDs, would be to set up the duty cycle mode, and then you can just put in a value into your FRQ A or B register that you calculate is the amount you want, and then that will cause the output to have a given pulse width.
So can you do a quick 1 second review of how counters work with freak and PHSA and all that?
Sure. So
magic.
So depending on the modes you set, and the modes we're talking about are typically the either NCO or duty modes, and usually single-ended, but you can also use differential, and differential just means that one pin will be inversion of the other pin that you assign to the output. You can assign 2 different pins.
Okay.
And you can mix those together to dampen the result, which is awesome.
Complicating.
Right.
Sorry.
So with NCO and duty cycle modes, the system is set up such that every system clock, the value that is in FRQA, for example, is added to the value in PHSA.
Yep.
And that value will just count up, and then when it fills up the 32-bit thing, it'll wrap back around to 0 and keep counting up and wrapping back around.
Okay.
Right? And then in the NCO mode, it just uses the state of that 31-bit, the top bit of that PHSA register.
Mm-hmm.
Whatever state that bit's in, that's the state the pin is in.
Okay.
Right? Whereas in duty cycle mode, it uses the state minus the carry. It's a little more complicated, but you end up with the getting a duty cycle out instead of just a straight frequency out. And you go back to our episode where we discussed that, because we could spend a whole nother episode explaining all this again. But it has to do with just the way that works causes you to end up with a duty cycle output, which is what you want.
So how I'm going to reference you guys now to look at the Parallax app notes. And if we can cover page 5 for the duty cycle biz. So every clock cycle,
page
FRQ,
page 5 is for NCO.
Oh, all right.
You want to scroll down to the page, what is it, 11, I think? 12. Page 12.
12. Okay. All right, I'm in 12. So for every clock cycle, FRQA is added to PHSA. When PHSA wraps around, that is the conclusion of one cycle?
Yes.
Okay. So
you will have, in the time period of PHSA going from 0 to maximum and wrapping back around to the 0, you will have some percentage of time on and some percentage of time off. And that is all one square wave cycle.
Okay. All right. So then here, can you tell us what we're looking at?
So what this is just trying to represent is different values that you would plug into FRQA that would give you different duty cycles over time.
Okay.
So like the bottom of that little table shows a lower value, and that equals a lot of time off and only a little bit of time on.
Mm-hmm.
Right? So they're showing a big gap and then a little pulse up.
Right.
And then as you go up the chart, it's just more time on and less time off.
So 1, 2, 4, 8, that just doubles.
Right.
And then we go to A and then C. And how far up does that go? Does it go to like Z?
You can go all the way to F. No, it's just hex, right?
Oh.
So A is a 10, C.
C is 12.
Very simple.
I see.
And you get to F, 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 F. And if you plug in F, 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 you're just going to get a constant on.
So 100% duty cycle.
Right. And if you plug in 0, you're going to get all the
0% duty cycle.
Right. And if you put in a really small number, if you just put in 1, right, at the bottom, it's going to go, off for a really long time and then on for a little teeny tiny short blip.
Sure.
That will probably not even register on the pin unless you had a really expensive logic analyzer to see it.
Right. So one of the more complex things that we were trying to address last time was sound generation. And with sound generation, I mean, we know that there has to be a low pass filter circuit after this signal, this pulse width modulation, right? Is sent from the propeller, right?
Right.
But the interesting thing about the pulse width modulation involved in sound generation is it gets like wider, like the duty cycle gets larger and then it gets smaller, say for a sine wave.
Right. And that you accomplish that by just continuously updating your FRQ register, right? FRQA. If you just keep changing the value and you make it smaller and then bigger and then smaller and then bigger at the appropriate rates of time, then you'll create a wave shape out the other side. So, and you could do a simple one, which is, a triangle, or you could do a sawtooth, or you could do a sine wave, or you could do a wave shape like a recorded wave sample.
Right.
And it's just all a matter of controlling that FRQA register.
So then do you say like FRQA equals
you assign it values, and you write a program to determine what those values should be. And that's where the magic, or where you do your work to make it do something. You
remember last week how we were talking about how your duty cycle over time averages out to be a voltage on the other side of the low pass filter?
Yeah.
You're setting that number, that FRQA, to change the averaged voltage coming out the other side.
I understand, but I mean, would you write it like FRQA equals $1 million or 100, 10 million or whatever?
What you probably do, like there's a couple of simple ways to do it. One is you could have a data table in your program, which is just a bunch of values to feed into FRQA one after another. And then you would just have a little loop that would read the value and plug it into the FRQA and then read the next value.
You may remember when we talked about the ROM on the prop, that there's a sine wave table. Well, part of one anyway, but you can use some math to flip around the part that's there to get the whole thing.
Oh.
Right. So you could write a program that would take the sine wave table that's built into the ROM and turn it into values to stick into FRQA, and using a little bit of math create the entire sine wave shape, like Whisker alluded to. Mm-hmm. And then you could play that at faster or slower speeds to get different frequency sine waves.
Boop, boop.
And then how would you determine that? Like, how would you make it faster?
You would use some math based on the clock speed of the processor and how fast you're able to update your FRQA. Like in spin, you wouldn't be able to go very fast.
Okay.
You wouldn't get to super high frequencies. You'd only be able to do medium to low frequencies.
Yeah.
Which is why when you would want to use PASM to get the best quality, right? But for a good quality shape to your sine wave, right, that has a nice shape, you want to update that FRQA register as fast as possible. And in spin, you could get pretty decent update rates if all you're doing is that one thing on a cog is just updating it with the shape of the wave.
Mm-hmm.
But you're still not going to get as high quality as if you wrote it all in PASM.
Yeah.
I wanted to say something.
Spin is fine for doing like pulse width modulation out to something simple like, say your servo stuff that you're talking about, not exactly PWM, but
Well, let's say LEDs. Let's make it easier.
Spin is fast enough to do that fairly well. Yeah, you could do it with LEDs. A camera will probably see some flicker, but because the human eyes are so slow to update, you won't see a flicker until you get way low.
Well, here's the thing with an LED, if you set the FRQ register to some value, it's going to continuously output that duty cycle. So the LED will will be pulse width modulated at the given percentage on, percentage off rate.
Right.
And it will look dim or bright depending on what you set the value to.
Right.
What you will be limited in with spin is how quickly you could fade the LED in and fade it out, right? You would have, in spin, you'll have slight steps where you're going from one to the next, whereas in PASM you could go really fast. It would look more smooth.
I see.
Now, and you can do this without a counter. I did it for the podcast clock project. Mm-hmm. I managed to get the PWM working without using a PASM object, and managed to fade it in and out fairly smoothly without using any ASM. So yeah, you can do that in spin because we're just dealing with on and offs. But Addie's question about with audio, you're talking about you have to be up at least, several kilohertz, because of the Nyquist thing. But something like the propeller signal generator that we talked about last week is actually running at like 20 megahertz of samples. Right. So it's got very high resolution.
So you wouldn't be able to code that in spin?
No.
Oh,
but again, with an LED or a motor, you could use spin to drive it using the counters to help you doing this duty cycle. You could use spin to get pretty good control. And when I was alluding to you would have slight steps, those steps would like only be visible on, say, like a scope or an analyzer looking at them. Visually, you would probably not even be able to perceive the steps. It would look very smoothly fading in and out the LED using just spin to update the FRQ register. Again, for LEDs and motor controls and whatnot, the rates are plenty fast enough. It's audio, it goes into a new realm because you're not only are you setting the register a bunch, you're setting it to create a wave shape, which you then need to go at some frequency so you can hear a nice sound. And obviously for like 440 hertz signal, you don't have to go so fast. But if you want to get a nice, high frequency signal with all the harmonics factored in, then you're going to need to go at a really high clip, and that's going to basically require
it's no small feat to generate a 1 megahertz sine wave digitally. The fact that you can kind of do it fairly cleanly with a prop is very impressive.
Okay. So I wanted to say something for the newbies, because when looking at tutorials for duty cycle, it almost looks like it's one block of on and one block of off. Like it looks like a S-shaped curve or whatever, right? Give or take. But I'm realizing now, when looking at this figure in the app note, that each of these waveforms are one cycle, and all of the on peaks add together to form what the total percentage of duty cycle is. So for instance, the lowest one, that's like maybe, I don't know, 5% duty cycle. The second one is 10% duty cycle. Third one is, I don't know, 30% duty cycle.
20. It goes 10, 20, 40, 80, it goes up.
Okay. So then
doubles each time.
Okay. So 10%, 20%, 40%. But like at first I thought, the second one has 2 cycles and the third one has 4 cycles. But no, like the waveform is 1 cycle, and all the peaks, the on peaks, are the duty cycle portion. So I thought just for anybody, I thought for anybody who was like, what, then that might help to.
And there's a little bit of math you can use to calculate, and they go over it in the app note there that you should have a link to in the description. Of what values you can put in FRQA to get what duty cycle you want out the other side.
Okay. So I think that's a pretty good reintroduction to the ideas of using the counters to do PWM. Or are there other questions?
Yeah, so let's see here. SoftCon said quick tutorial type shows on getting some of the many third-party languages installed on the propeller would be something to cover. So I think
we're going to be doing a prop GCC thing here soon, so we'll get to that.
Yep.
Yeah.
And what other languages
there's a couple of different compilers. There's the Catalina C, there's prop GCC, there's a fourth language. There's even what was a Zog, which is like a whole CPU emulator which can actually run GCC variant. So it's like it's not very fast, but it's out there. There's a bunch of people doing a bunch of different languages.
Okay.
Some of which are not necessarily user friendly for noobs. They're kind of advanced, but at least with Prop GCC, there's simple IDE, and there's a lot of people on the forums willing to help. And Catalina is not too bad also. The guy out there is supports it pretty well and helps people get set up. So
Gotcha. So yeah, we'll go more into Prop GCC again in future episode. Local Roger said he actually asked about pulse width modulation again, and suggested show using counter control true
pulse width modulation. Everybody's talking about pulse width modulation.
Well, it's because I didn't fully realize that I didn't actually get it. I know what duty cycle is in and of itself, and I know what servo type pulse width modulation is, but the mixing of the two is like what? Just nut bar.
So we kind of covered Local Roger's question, first one there, pretty well. I mean,
and don't tie up a cog.
Yeah, well, that's the whole idea of the using the counters to do it.
Because the counters keep doing their thing, you know.
Okay.
Once you set up the register to output a given duty cycle, it'll keep doing it until you change it to do something else.
Okay.
Right. So.
And then Local Rogers number 2, using high EEPROM to save non-volatile values.
I want to do this too.
So what he's talking about there is if you have a lot of the propeller boards have an EEPROM on them that's bigger than the 32K that's normally used to just load up the propeller with the default program that you program into it, and you can use I2C commands to talk to the EEPROM device.
Hello, EEPROM. I am propeller. Will you save some things for me?
On pins 28 and 29, and you can write to those upper addresses.
Okay.
And do, store whatever you want up there in those.
So if you got like a 64K EEPROM, you've got, 32K of empty space just sitting there that you can use to store the variables and whatnot in between runs of your application.
And the propeller won't overwrite them. So by default, when you download a new program, it only rewrites the first 32K.
Oh.
So you can actually store data in that upper 32K in the second bank of 32K, and they'll stay there from update to update until you write code that actually changes them and reads them back and does stuff with them.
Now, Wesker just said you can store variables, but wouldn't variables, like constantly changing variables, be considered volatile values?
Well, right. So what he means by non-volatile is just that the fact that they stay up in that EEPROM, and if you turn it off and turn them back on again, you can read them back out of the EEPROM again, and they'll still be. So it's
more like the sort of thing where it's going to be saving something to that slot every so often, and then when the thing powers back up after being disconnected or whatever, it pulls it back out, so it has that to start with, like user settings and stuff like that,
So then, do you have to point it at a specific spot in the EEPROM because it's non-traditional?
Above 32K.
Right.
Well, it's all traditional. It's just that you're addressing the second 32K of memory instead of the first 32K. So the first 32K has your programs, and
the PASM program that automatically gets loaded into the cog, as she's coming online, it only reads
the first 32K.
The first 32K.
I get that. Yes, I get that.
Right.
It doesn't ever.
And the high EEPROM is referring to the second 32K.
Or whatever.
In the example of a 64K EEPROM.
It could be 128.
Or 128, right. Okay.
However much memory is up there. And when you talk to an I2C device, you tell it what address you want to read or what address you want to write.
Oh, it's that read-write
thing. It's just like any other I2C device, like we've discussed recently talking to your sensors, right? It's the same thing.
So then could your sensors, because your sensors are I2C, could they hook to pins 28, 29 and then send their data to the
well, they wouldn't do
higher
it directly.
EEPROM?
No, they're not going to do it directly because they're not a master device.
I see.
Your propeller could talk to them on pins 28 and 29 if you wanted to, and read the sensor and then write it back out to the EEPROM.
Okay. And then could something else read the EEPROM and send it elsewhere?
Yeah, some other program could read the EEPROM and do something with it. And you could like one of the things you could do is you could save the last time you read the altitude. You could save it in the EEPROM, and then the next time you run the program, you could read what you read last time and read what you're getting now. And
bigger than a certain delta, you could have your MX say, "Oh crap!"
Okay, wait. So I have a question. So say I want my altimeter, my GPS module, my compass to all send messages, or to send their states, their most updated states, to the prop, and which sends it to the high EEPROM, right?
Hey, Roy, well, I think that one went over Addie's head. Get it?
Because you're distracting me. Okay, so when it goes to high EEPROM, do you have to direct it to like a specific spot in memory, like PASM style?
No. In spin, I mean, you're just doing
like.
I2C
Give me an
command.
example of how you would write it. Like,
so you would do an I2C write command and tell it the address in the EEPROM, the actual memory address,
like $ AC or something.
Right, whatever address you want it to be, and it would have to be a large number, right? Because you're dealing with the over 32K.
So as long as you knew that address, you can always have the same data, replace the same.
Eddie, you get that addresses are just numbers. It doesn't have to be in hex or binary or decimal. It doesn't really care. It's just easier to write it down in hex.
So I could do write 10 million.
Right. Mm-hmm. If the EEPROM had 10 million addresses in it, then you could write to the 10 millionth address.
The propeller typically does not care what base you write a number down in, because it's all the same in RAM.
So at one point.
So let's do the basic example. You have a 64K EEPROM in there, right?
Yep.
If you wanted to, you could write a program that could use I2C and write to address 40,000.
Yep.
In that EEPROM, and at address 40,000, it would store your value.
Yep.
And then next time you booted up the propeller, if you read address 40,000 from the EEPROM, it would be the value that you saved last time when you wrote it out there.
Yep. And while I was in the Parallax manufacturing facility, they gave us a tour.
Yeah.
I put secret messages on all the EEPROMs. I'm not telling you the address though.
Liar. You did not.
You can't prove it.
I videotaped our tour.
Yeah.
You weren't that sneaky.
So I was with Joe Grand. You're really going to put it past Joe and I?
There are some objects out on the object exchange that actually do this for you automatically, but you don't really need the object.
What's the point, though?
I mean, you're just doing basic I2C commands. So if you're just storing like a single byte or a few bytes of data, then you could just write some I2C values to just output a byte at that address and read it back.
My use case for this was in my SIDCOG organ. I'd like it to remember all the settings last time I was using it. So if I've got my, it's set to make triangle waves and, the filters are set with the roll off at blah, blah, blah. It'll just save all that information and load it right back up.
I have a question.
Yep.
So your program, I know this is probably going back to the beginning, but your program, no matter how small, will take up the 32K.
Yeah. So what happens is that when you download your program into the propeller and tell it to save it to the EEPROM, it takes its entire 32K of memory and writes it out to the EEPROM.
I see. That's right. There's like a whole bunch of blanks.
And so there'll just be a whole bunch of zeros for a lot of it.
Okay. I get it.
All right. Next question.
Do we have time?
We've got 2 minutes. 1 minute.
Real-time clock like DS1307.
Real-time clocks are great.
What's DS1307?
So it's just a particular chip that is a real-time clock.
What protocol does it talk?
As opposed to a fake time clock?
Well, real-time clock just means that it keeps real-time because it has like a battery backup and a crystal that goes
even when your propeller is off, it's still keeping time.
I see.
Now, what do they speak?
And I believe the DS1307 is an I2C device.
So you would just do it the same as most of the modules we've talked about, or the EEPROM.
And they have SPI versions and simple serial versions, which are even more simple than SPI. But
okie dokie.
That's all that is.
Do we answer that though? I mean, How do you use real time?
We could probably do an episode specifically on
real-time clocks.
We just
stuff
need
you can do with them. We don't have time to sort of get into details here, but
because I don't know.
We'll have to get you one. It's just a chip that we'll have to get you, and you have.
There's one on that big dev board that you sent over, Roy. So.
Oh yeah. There you go.
Let her play with that one. Okay, that's all the time we have for this week. Thank you, everyone, for listening. And find the Parallax Forum thread if you have any questions that you'd like us to answer.
Add them all
on the air. We'll get to them as soon as we can. You can find this show every week at firstspin.tv. We put it up Tuesday evenings. There's an RSS feed there. You can automatically have it downloaded through your iTunes, your phone, whatever. It's real easy. You can also listen to it right on the page. Just click play. All right, that's it for us.
Ciao.
Bye.
Take care.